I figured, yeah, number 10 was like full of lots of arithmetic work. Oh my gosh, she's alive. You're alive. Hello, how are you?
I'm good. How are you?
I'm good. I'm good. All right, so 10 was a lot of steps, so I did it. I couldn't do it with the big thick markers. It just took too much space. Is that readable? Yeah, there was just like number 10 just had so many pieces to it. Lots of unlike denominators. It just wasn't fun. No. But in a situation like that, realistically speaking, what I would expect you to do, unless, I specifically gave you a reason why, this is the kind of problem that you use a calculator for. You set up the integral and you solve. You don't bother with the big long process of it all. Okay. So that was number 10 in all of its ugly glory. Here were the others. Since we've already seen 10. Some of them we did in class, so. Anybody want to pull another one out? Anyone have issues with number 9? Anyone do number 9? Yes. Anisha, you have a question, or are you saying you did it?
Can you put the paper a little lower? Like, what's the answer?
The answer to...
No, for number 9.
Number who?
Number 9.
5 or 4.
Okay, yeah. Can you go over that one?
Sure. All right. So that one was wrong marker. Oops. That one was y equals x. Was it to the 2/3? Yeah. And it's something that looked a little bit like that. And we were interested in this region. Now, and we were revolving about the y. So if we're revolving about the y, then we have to have our integrand in terms of y. So x is equal to y to the 3/2. And then we're integrating from 0 to 1. And that's just y cubed, which is pi y to the 4th over 4 from 0 to 1, which is pi times 1/4, or pi over 4. The thing to remember is that when you're revolving about y, you want to make sure that your integrand is in terms of y, which means solving for x. That's the key when revolving about y. All right. Okay.
Did you go over number 4?
Sure. I'm gonna have to look that one again.
Like the half sphere.
Okay. So uh, 0 to 3, and you're revolving about x, and you have y equals the square root of 9 minus x squared. And so my integrand is from 0 to 3, because we're going about the x-axis. And so it's square root 9 minus x squared squared dx, which is pi 0 to 3, 9 minus x squared dx, which is pi 9x minus x cubed over 3 from 0 to 3, which is pi 27 minus 9, which is 18 pi. What happened?
I mean, I sort of got confused. I thought we were supposed to. I thought I was supposed to use like the half sphere thing that you talked about.
Oh, you absolutely can. I mean, this is how you would do it using calculus. But what we're dealing with is we're dealing with the volume of half of a sphere, right? As you correctly pointed out. And the volume of a sphere is 4/3 pi r cubed. And since we're only dealing with half of it, it would be 2 pi r cubed over 3. And then plugging in my radius of 3, that would give me 27 over 3, which is 9, and times 2 pi, which is 18 pi. Absolutely. You can do it with calculus, or you can do it with geometry. What's up, Kevin?
I mean, like, I kind of feel dumb because I use it to integrate. Like I use that formula and I
Oh, you
integrated
use
that.
2 pi r cubed over 3 to integrate. Oh,
Yeah.
gotcha. Yeah, that would give you something different. Yeah. Okay. Now, so what I want to talk about today is we're going to go back into the disk method, talk about that for just a few moments. But we're going to be talking about axes other than the x or y axis. Okay. Now, this is really a lot like some of the other problems that we talked about actually on Tuesday. So let's say I was revolving y is equal to the square root of x plus 2 about the line y equals 1. Okay. So if we were to graph that, and we're going to go from 0 to 4. Okay. And what we're basically getting here is this block. Okay. Now, going back to the Riemann sum, viewpoint of this, we are talking about that block, that little rectangle, being spun around this axis. Okay.
Could you like take the y equals and move it down one
That's exactly
to
what
change
you do.
the equation so that you
That's exactly what you do. You modify your function, because what you're saying is you're saying upper minus lower, which produces and then that gets squared. So what we're basically talking about here is if we simplify this, we wind up with just x plus 1. And x plus 1 is the exact same shape, except now instead of revolving about y equals 1, we're revolving about the x-axis. And if you simplify that, that's what you get right here. Okay. Another way of doing this, which is very, very similar, is sometimes your function and your axes intersect. So if I was doing, how about this? I'll tell you this. Y is equal to the square root of x about y equals y equals 1, and bounded by x equals 4. So what I want you to do is I want you to imagine what that image looks like. Draw a crappy picture. Okay, draw this guy, draw that guy, and then create the integral where this guy's revolving about the line y equals 1. So here, this is what you're being asked to look at. Okay. But conceptually, what you can do is take this function, slide it down 1, and go from 1 to 4, which again gives you the exact same integral, by the way. So let me give you a more complex problem. Y is equal to the cube root of x about x equals 1 and bounded by y equals 2. So let's start by drawing the functions. We got a cube root. We have x equals 1. Y equals 2. And we're talking about that block of values, that block of area. And when that thing spins around x equals 1, it's going to look like something like that, like a weird looking top, but it'll be circular. You see? So we can do this. Now, first of all, we realize that what we're dealing with here is revolving about the y-axis. So let's take this function and move the axis of rotation, which is x equals 1, over to the y-axis by looking at this guy and saying, okay, instead of this guy, we're going to write what? How do I take him and move him like that?
You add 1, so it'd be the cube root of x plus 1.
Do I put it inside or outside the parentheses?
Inside.
Inside. And you see now that would be the function that we would be using to spin around the axis. However, do we write our integral right now? No, what do we have to do before we can write our integral?
You have to solve in terms of
y.
Yes, it has to be in terms of y. So the cube root of y, or y cubed minus 1 is equal to x. And that's going to be my integral. And my y values are from what to what? What are my bounds?
Yes.
1 to 2.
Good. And you see, that's the exact same thing as if I had taken this guy, solved it for x and gotten y cubed, and then gone y cubed minus 1, I would have gotten the exact same integral. You see, because I'm going to be going from outer to inner. How does that feel? Okay, cool. All right. So now let's talk about a similar idea, which is called the washer method. And this is when we revolve that you are not touching. So let's think about this for a second. Let's take that square root function that we dealt with before. And we had the line y equals 1, and we had this area. Now, in the example that we did before, I was revolving about x equals 1. So what we're going to do here is we're not going to revolve around x equals 1. We're going to revolve around the x-axis. And if when we spin around the x-axis, we're going to get a shape. This guy's going to be on the other side. And we're going to wind up with a shape that looks like that. It's going to be solid, but it's going to have a hole bored through the middle of it. Now, in order to make this and find this, what we do is we make it the same way we would make it if you were actually in a wood shop or a metal shop. You would make the outer shape you would make it solid, and then you cut out, using a drill, the core. Because what we have is we have an upper curve and we have a lower curve, and by finding each of their volumes and then carving it out, we can find the volume of what's left over, which is what we want. Does that make sense conceptually? So really what this means is that we can set this up with two integrals, a positive integral and a negative integral, and then subtract them. Now, sometimes it's easiest to just do it that way. Other times it's easiest to combine them, meaning that if I was to actually do this problem, it would be the integral of the square root of x squared from 1 to 4 minus the integral from 1 to 4 of the core, which was just y equals 1. Okay. Now, this problem, if I were to combine, I mean, first of all, this is nothing, right? I mean, this is, you know, pi r squared h, so this is 3 pi. Okay. But this is, you know, really straightforward. It's just x squared over 2, and you plug in 4 and you plug in 1, you get 15 pi over 2. And then you would subtract your 3 pi from that and, you know, wind up with 9 pi over 2. Okay, but the point is that this is very straightforward, but this is the idea. Now, if I wanted to, I could have written it just as easily like this. Okay, now, this is kind of silly. There's really no real need for it, right? Because all we're wind up getting is pi over pi minus 1. But in an example later on, we're going to see that sometimes this is a preferred way of doing it, because then you'll have like terms that can combine and simplify. Okay, but oftentimes you don't have like terms. But this one, we don't have like terms. But if we had another problem, like we will in a minute, we'll see it, okay? All right, so let's use,
Ronco,
yo.
I have a doctor's appointment, so I have to go.
Okay,
All right, bye.
take it easy. I'll post a video.
Okay, thank you.
Sure, bye-bye. So let's use y is equal to negative x squared plus 8x plus 2 minus 10. Whoops, sorry, minus 10. And the line y equals 2, and we're going to go about the x-axis. So just to show you what we're dealing with, I'm going to go ahead and share my screen wherever the heck it is. Hold on. One moment. Okay. Volume. Okay. So hopefully you're all looking at a GeoGebra file, right? Okay. So here is the parabola that we're talking about. Here's the line y equals x. Sorry, y equals 2. Okay. And we're revolving about the x-axis. So just for a second, I want you to take a look at what you're looking at and imagine what the shape would be if this curve spun around the x-axis. What would it kind of look like?
A donut.
Almost a donut. It would have a hole in it, right? Let's see it. So what we've got is we've got this shape that kind of looks like maybe like a squished ball or something with a hole cut through it. You see what I mean? It's like if you were to take a very soft rubber ball, squish it down, freeze it, and then drill a hole through it. Okay, you get this strange looking shape. Okay. Now, what I want you to do is to set up the integral to find that volume. Now, don't solve it, just set it up. Did we get that integral?
How do you figure out what the bound would be?
Good question. So negative x squared plus 8x minus 10 is equal to 2. So moving over, we get negative 12. Divide by negative 1, which factors into x minus 2 and x minus 6 equals 0. So x is 2 and x is 6. Find the points of intersection. Yeah. Now, if you had to do this as like a problem on a test or something, you could theoretically do this by hand, but ooh, would it suck. What you do instead is you put this in a calculator. You know, you use Math 9 for this, right? We've covered that, haven't we? Everyone have their calculators handy? Yeah, you can do it using Math 9. If I can get this to focus. There it is. And then you would just subtract them to get 84.8x, 84.8 pi. Okay, yeah, use the Math 9 key. And you plug in all your stuff. Okay. All right, now, what if we wanted to take that exact same shape, but in this time, we want to revolve around the y-axis? So let's first ask ourselves the question, what are the bounds? Okay, so we know that this is 2, we know that this is 6. How do we find this? Remember, it was y is equal to negative x squared plus 8x minus 10. 2 ways we can find the top of that value, the top of that parabola. How do we find it, people?
Isn't it just the maximum?
It is. So how do we find it?
You could graph it.
You could, but right now, without calculators. How do we find maximum and minimum before?
Can we plug in 4?
Why 4?
Because it's the that's what the highest point would be if x equaled 4.
You're exactly right. How did you know that it was 4?
It's the number in between the two bounds, x equals 2 and x equals 6.
Right, because it's a symmetric parabola. The focus, sorry, the vertex has to be in the middle, so it is 4. Or you just take the derivative and set it equal to 0. Negative 2x plus 8 equals 0. X is equal to 4. Okay, so you plug in 4 and you get negative 16 plus 32 minus 10 minus 26. So x is 6. Y is 6. So that's something you're going to have to know to do. Now, our Riemannian box is going to have this as the outer and this as the inner. So what we have to do first is get this guy in order to integrate in terms of with respect to y. We have to get this guy in terms of y. So we have to solve this thing for x. How do we do that? How do we solve a quadratic in terms of x?
Completing the
Could
square.
you the
The square.
Completing the square.
Complete the square. So negative x squared plus 8x is equal to y plus 10, right? Now we're going to divide everybody by -1. You guys know how to finish the rest? Okay, we good on that? Okay. So now, this is a situation where we really should be able to simplify our integrand a lot. Because if we do from 2 to 6 of 4 plus square root 6 minus y squared dy minus pi 2 to 6 4 minus the square root of 6 minus y squared dy. Before we go anywhere, one thing that you should realize is that once I expand out this odd-looking quadratic and this odd-looking quadratic, we're going to have a lot of things that cancel out. So let's go ahead. We'll expand it and put it all under one integrand. Now, looking at this, you'll see immediately that a number of things start to cancel out. The 16 minus 16 is gone. The plus 6y minus plus 6y is gone. But these two, since I've got a negative and a negative, these two are going to combine. And now we have a much nicer integral. And you can do a u sub, and everything boils out really nicely. In fact, I've already done that. And you wind up with now, just for fun, to show you what it looks like. What would it, by the way, what do you think it would look like if we spun it? Which shape do you think it would take? If we spun this around the y-axis. Any guesses? What does that look like? Has never seen a pound cake or a bundt cake or Jello mold?
I thought you meant like actual shape, and I don't want to say something dumb.
All right. Actually, if anything, it you know, that isn't culinarily related. I would say it looks like the front end of a jet engine. You know, where air flows in and over. You know, but you know the blades of the fan would be on the interior, but of course it wouldn't. It would be a much narrower parabola or a wider radius in order for that to work. All right, so I'll put out some problems for you guys to do. Nothing too bad, nothing too much, and you guys take it easy.
Oh, Ronco, what do you want us to do with the textbooks? Because I know some students have to turn it in.
Oh, snap. I don't know. Let me email the lady who does all the textbook stuff. Here's what I would say with that.